Hi, this is Nalini Elkins with Industry Network Technology Council. Welcome to a webinar on CDNs with Igor Lubashev of Akamai. Let me give a couple of words about INTC. We are a nonprofit organization that promotes internet standards education and the research that is going on around it. So we partner with the India Internet Engineering Society, which aims to do capacity building in India, and they have been quite successful. We have done quite a bit this in the past few years. We did a multi-year IPv6 deployment at Enterprises Series, which was funded by Aaron and APNIC. We did quite a few webinars on security. And for this year and next, we will be focusing on new work at the IETF and also how some very important components such as CDNs affect this whole arena. As I say, we have received a number of grants from both Aaron and APNIC. Thank you so much. A couple of words about me. I'm a geek and I write products for a living. My life has been ill spent. So a few words about Igor. He is Director of Engineering at Akamai. He has done quite a bit with the Linux kernel and OS, Edge Virtualization, all the kind of stuff you might expect as at CDN. And actually, I'd love to have him talk about anycast. That's a very interesting area that few people really get into. He's very active, of course, at the IETF. Has contributed to QUIC, as well as I believe SavNet. I believe that's what he's working on also. He has worked at Oracle, worked at startups, and is a graduate of MIT. So thank you very much, Igor. I'm going to stop sharing and off to you. Thank you so much.
All right, let me set it up here. Should be able to see it now. Okay, well, thank you everybody for joining us. I hope it will be an interesting hour. Like Nalini said, and thank you Nalini for this wonderful introduction. I work for Akamai. My goal today though is to cover topics that are going to be common across all CDNs. I know Akamai the most, so it may be there will be some things that are Akamai specific, but I will try to point that out. It's going to be a pretty fast-paced hour. CDN is a big topic, and so let's dive into it. So, how does internet work? And if you ask a layperson, they'll probably just tell you, we have computers connected to this cloud internet, and there are some servers connected to that cloud, and they just talk, and that's how you get your data. That's how you get your web content. If you talk to somebody who knows a little more, they'll know that internet is really a connection of independent networks, like your devices at home connect to ISPs that connect to the cloud. And that's pretty much how internet did work. And that's how you get your web content in 1990s. And this is how websites looked like in 1990s. You can see basically a single HTML page with very minimum number of media or other things, just a single page website. Fast forward by 5 years, and the websites are getting way more complicated. You have many pictures, half a dozen to a dozen different pictures on the page. You have just a lot like bigger pages. And if we look at the statistics about internet growth, so the first one is So the page itself, the front page, maybe have grown just a little bit, but the number of objects on that page is growing a lot, like we saw. The number of people who are using the internet is growing quite a bit from 1995 to like 1999. And what's interesting was the log scale. The speed with which people are connecting to the internet is growing exponentially. So coming from dial-up modems, if people here remember such things, if you're kind of my age, to much more modern technologies, DSL and then cable connections become prevalent. So we have more people trying to download content at much higher speeds, and the content is much bigger and much richer. What is the effect? It's effectively congestion. Congestion in the middle of the internet in those transit networks. And that's also not only slowing things down, it's also costing a lot of money. Money to the ISPs, because they're paying for every bit delivered from this from the transit networks. It's costing money to the content owners, because they're paying for every bit delivered from their data centers. And in the end, it was like in 1999, kind of common to wait for your web page to load for like 10 to 15, even 20 seconds. Right now, it's like absolutely crazy, but that's how it was. And there was a term coined for WWW, standing for worldwide wait. So how can we fix it? This is where CDNs, when CDNs were born. So 1999 is the birth date of the very first CDN, that Akamai Technologies, the place I'm working on. The idea was a lot of that content we've seen is very much the same for every user, especially the media, which is the bulkiest part of it. Cache it next to the users. Don't keep downloading from the data centers. Deploy a number of servers very close to users in all the ISPs and prevent this congestion, serve it better. Essentially, CDNs were helping everybody, pretty much everybody involved. You have end users. Well, obviously, starting with the data center content owners, their content is being delivered faster, and they're paying less. So they're CDN customers, but also the ISPs were CDN partners quite often. In fact, I remember cases when some, for whatever reason, pub inside one ISP, small ISP somewhere in South America, stopped working. We got a frantic call from that ISP saying that, can you please get your pub to work again, because we're losing money. Our data is going basically, all the content that users are asking for is going through the transit network. We're losing money. We're paying the transit network for all these bytes. Get your stuff working back online. And of course, it's good for the end users. They're getting much better web experience. Now, as with everything good, like internet, there are always people who trying to take advantage of it and make it bad. So with the rise of the internet, it was a rise of attacks against web properties, against other things. The typical way to defend against attack before CDNs was that you have firewalls or something at the data centers. So you have your distributed botnets of compromised machines attacking a single data center property, probably taking it offline because that attack would exceed capacity of how it's connected. And by the way, in the middle, there could be casualties like entire ISP if it has a lot of botnets behind it, may even get congested its connection to the rest of the internet. So it's not just this particular website that would get offline. Everybody in that ISP would suffer. And of course, it would cost money because every bit of that volume traffic delivered in both directions is costly. CDNs would be a natural place, was a natural place, as a natural place to help that. You have a distributed network close to the end users. They absorb the attacks. So the attack doesn't have to go through the transit network to the data centers. They basically terminated CDNs. They have a lot of capacity. Because of distributed nature, you have basically different botnets are really attacking different servers. And the CDN itself can be smart enough to direct good traffic to servers that are not being attacked right now under load. And that's basically been great for content owners because the data centers stay online, better experience for everybody. All right, fast forward 2007, and that's basically the rise of what we call a streaming media. So again, internet is great. More users, people are finding more users to it. Instead of watching videos on TV and in the movie theaters, people start to watch it online. It's both with live events and with pre-recorded videos, so basically Netflix of this world. And one of the graphs I found is the US streaming video revenue per year, but basically that corresponds very closely to the number of videos streamed. So basically number of titles, number of hours of video consumed. And you can see that's basically been growing linearly. Now, the other thing that's been growing, and that's actually more than linearly, kind of exponentially, the quality of those videos. Like from 2007, where we were basically having DVD quality videos, to right now when people are streaming 8K videos sometimes. And 4K is ubiquitous, 8K is now actually somewhat common. And the speed with which people's internet connection is being provided to them has also continued to grow. So we have right now from 2007 till now more people watching, much higher quality, so more bandwidth, more bits videos, and the home networks, the edge networks are able to support that volume. What does it mean for CDNs in terms of like how we're describing it here? While they may be able to still stream the videos from the edge, the library size, so the more people watching, that means long tail content has been streamed, and all the content is bigger. The content, it doesn't really fit inside those servers and those ISPs. So what CDNs do is effectively multi-tier distribution, which means the most popular content is cached at ISPs. The less popular content is cached at much bigger locations, much fewer locations, but much bigger locations in well-connected points in the internet. Still much closer than the original data center. Okay, well, two questions. First, what about the content that cannot be cached? And also, what about the content that is not present in the at the edge and now needs to be loaded from the origin server? Can CDNs help here? Now, without CDNs, we are just relying on internet routing, and internet routing is controlled by BGP protocol, Border Gateway Protocol. That's been the protocol that's been used from the beginning of the internet, pretty much. And the goal of that protocol is to route your data along the shortest path. In BGP's understanding of the shortest path, which means fewest autonomous systems along the way. Now, that's also kind of optimistic. Each network owns its relationship with other networks, and sometimes networks will not even follow fewest autonomous systems away because of business preferences. But what's most important, BGP doesn't mean fewest hubs or like lowest latency or least congested path. If a path is congested, BGP is not aware. So BGP is very happy to route you through a congested path, even if there is another path that's available, maybe a few extra ASs away, but your traffic will just get routed through congestion. And here where CDNs can help. So if you have a CDN node that the end user connects to, and origin node that somewhere near another CDN pub, CDN can actually choose a path through which it can load the packet. It effectively either can do it directly through the internet or through an overlay network, effectively moving the packet hub by hub through its own network, through its own pubs. Now, multiple paths are always considered, and all of them are probed. So a moment, if an active path is starting to get congested, CDN can switch to another path, and the speed with which you can actually deliver packets will be still much faster. So example, just a particular case of between two locations in India sometime in 2018. So red line is the latency, effectively the loss, most likely due to congestion, on the path through the public internet. It's effectively through a BGP path between two pubs in location in India. And you can see that in a few days, there was quite a bit of congestion there, and loss reached up to 80%, which is like effectively untenable for normal good connection. While if you were going through our, like through Akamai, for example, because it's our data, you can see that the loss is pretty much negligible because we're routing probably not through the public path. And you can zoom in, you can see like at this point when congestion happened, probably the current path that Akamai was routing traffic from one place to another was affected. It was immediately spotted and rerouted through some other node. Okay, what other things can CDN help with for traffic that actually is not cacheable, right? Like we said, not everything is cacheable. Your bank account web page will not be cacheable because yours is very unique from mine, probably. So, number one, the CDN node that you're connecting to probably have already established persistent connections to each other and to the origin server. What it means is that we need to create fewer connections. And if somebody else, another customer is connecting, let's say, to the same bank and connecting to the same CDN pub, they will use the same existing connection. So no extra handshakes and no slow start is needed. So, and we can do multiplex many pubs through this. It's actually the same HTTP2 or HTTP3 connection. Graphically, what it means, so let's say this is a representation of our network capacity. So the red line is the throughput, theoretical maximum throughput that network can handle from. And if you're just using a normal single connection, you're connecting yourself without CDN help from one place to another. So first you have a TLS and TCP handshake happening, and then you have a slow start for a TCP or QUIC connection, which grows until it hits the throughput limit, at which point you have packet loss, at which point you have a the protocol cuts your throughput and it starts to ramp up again, at which point you hit a limit and so forth. So the amount of byte effectively that you are able to transfer during this point of time is the area of the under the curve. Now, if you have an existing persistent connection, you don't need to pay for TLS and TCP handshakes. Well, maybe you pay a little bit for the initial TCP handshake with a CDN server. But then you don't need to go into the slow start. The bandwidth is already known, and the amount of data you are transferring is significantly larger. It's, again, the area under the orange curve now. So, like we said, eliminate TCP slow start, eliminate handshakes, and also CDNs are in a business of performance. So it's possible, it's actually very likely that CDN's TCP parameters and tuning will be better suited than whatever edge device, whatever like personal device you are using now. Another thing that CDNs can help, again, in a case of end user accessing data that's maybe not entirely cached. So this is a typical scenario, 10 milliseconds to the edge server, 80 to the origin. You have end user sending a HTTP request. Edge server is processing it and forwarding it. But so, and then you get a response, an HTML page, which edge server receives. And it starts to parse it and process it just like your browser will, although it sees it sooner. It will return you the optimized HTML, so it can actually optimize HTML. We'll talk about it in a second. It may already have a few objects that HTML will require in cache, so it will do a push to you even before the web browser asks for it. So it's ready. And the objects it doesn't have and it knows it will need, it will initiate a prefetch from the origin server without being prompted by the edge server. So by the time not edge server, edge client, by the time the client parses the HTML, responds requesting additional objects, they're already probably in flight and they will be received faster. Once they're received, the CDN will return them and cache them for the future. So we're optimizing it here again. And CDN servers can also support JavaScript, and so they the processor here that processes it is quite powerful and can do pretty much everything that Edge client will do. This is a typical, we call it waterfall diagram, which shows a typical web page. So it starts with an HTML page and loads more objects, and so images, media, JavaScript, which may end up in requesting more objects and so forth. The green line is the line till the page looks rendered, and the blue line is the line until the page is actually interactive and can be used by the user. So it may start like that without any optimizations. CDN can perform optimizations just on the HTML, so we can a CDN can figure out which particular objects are actually not super important to interactivity, like for example, some sort of tracking cookies, move them to later, and optimize for things that will be visible on the screen. And it can also do things like maybe shrink, like reduce size of images and do other optimizations that are specific for this particular website. So effectively, we can take something that normally loads in 4 seconds and load in 1 second. This is a huge improvement to user experience. That's another thing CDNs do. Now, another, the websites today are not exactly the static pages that we saw in 1995 or even 1999, mostly. Today, websites have code that's running on the web servers that is generating you the web pages. Now, the stuff running in the web server, it could be accessing some very big database, and of course, it needs to happen on the origin server. But often, it's actually pretty simple stuff, pretty simple code that does not need the origin database to execute. The idea is move that code all the way to the CDN server before it actually, so it doesn't even need to get to the origin. That way, you get a response very quickly. So you get, by just moving the execution of customer of that code to the web server that's running like very close to the end user. So this is a kind of part of the menu that Akamai provides. Other CDNs do something similar. There are already pre-built snippets of code that you could basically opt into as a customer. You could do things like provide different behavior for if you know that if a CDN can detect that it's a bot or AI accessing your website, you can run some sort of A/B testing for your website for different populations. You could do phased releases if you have a website release and you want to like first give it to like some small portion of the population. If it's a busy website, we can do like some sort of a wait room for people. Often you see URLs that are kind of semantic URLs that kind of that spell out what's in a title of your blog article, for example. All of that can be done at the edge. It doesn't need a big database to access it, and it can be done very, very, very quickly. And of course, there is customer-owned code that you could write and have it execute right on the website, on the web server near the kind of CDN web server near the user. Another example is image processing. So media processing, really. Without CDNs, if a company, let's say it's a car manufacturer, wants to have a website with some pictures of their products, first of all, they need to maintain multiple sizes of each picture because depending what device and users are looking at, you want a different size. You might need different formats because different clients may prefer different formats for the media. Depending on the internet connection quality for your customers, you may need a highly compressed version of the picture if somebody has a low quality internet, or a high definition image if somebody has like very good connection. And it's possible that you might want multiple versions of the same image, maybe zooming in on some different part of the image and something like that. So a typical workflow would involve a lot of different people, a lot of different specialized software, internal databases, and content management systems to process and generate and update all these variants of the images, and then making sure that it serves correctly to the correct user. It really is a business in itself that somebody like a car manufacturer might not want to be in. For a CDN can help. All you need to do is provide the best quality image you have, and effectively CDN will take it from there. So media management is a typical product that CDN offers. CDN will make sure that correctly scaled, in correct format, with correct compression, image will be delivered to whatever the whatever is most appropriate for this end user. Simplify things a ton. And the same goes for video as well. CDNs can help with end-to-end content protection for videos, and it can make sure that whatever rights and geofencing is required can be done. Content owners can get quite detailed analysis on users consuming their videos, how they're doing it, where they're coming from, the quality of the network and quality of the video replayed, was there any rebuffering, anything like that. CDNs will provide as a part of a product for video delivery. Okay, next topic, and actually this is well, quite interesting topic right now, especially given the recent AWS outage, is DNS. Everything on the internet requires a working DNS platform. So there is nothing that CDN does that will be of any value to anybody if end users cannot get to the website. And to get to the websites, you need a DNS system that translates names into IP addresses. Akamai, and as every other CDN, is running a global network of thousands, tens of thousands of DNS servers all around the world. So the way DNS works, just a very quick primer, right? Your laptop, your phone is usually configured with a DNS server that your ISP provides, and your ISP server, or DNS server, we call it recursive server, is contacting the authoritative DNS server that is owned by the content owner, or a CDN which content owner delegated the DNS services to. And authoritative server returns the IP address which your ISP server usually caches, and returns back to the end user, and that's how end user knows what IP address to connect to. So the cloud of authoritative servers is usually done like basic in anycast way. So effectively there is like one or a small number of IP addresses that an authoritative server for DNS for the CDN will be available at, and many machines around the world, many locations around the world will announce through BGP to the internet that this IP address for the authoritative server is at this location. So effectively, the way BGP, the way it would work is that, yes, it will use BGP, but they will be available from many locations. So every single ISP will have a server. There will be many servers in the core of the internet. So wherever you are, there is an authoritative server belonging to the CDN close by. I don't know about how other CDNs do it. I mean, we run our own software at authoritative servers. We don't run open source software for it, mostly to make sure that we can have our own features, but also to make sure that we're not suffering from the common vulnerabilities that could be found in open source software. So, like I said, DNS is super critical, and as we've seen with AWS right now, that where it was a problem with DNS servers is a huge problem. So a lot of effort is put into, we don't have time for right now, into securing and making sure this DNS platform has capacity and security. Now that we've built DNS for ourselves, DNS is also available as a service to customers. Let's say you have a number of data centers around the world. So they're here in gray. And you can configure, let's say, a CDN's DNS service to point to the correct data center for a customer, depending what location the customer is in, for example. So if a customer is North America, in the East North America, it may point to Virginia, West North America, Los Angeles. If you're in India, you can point to a location in India. You can configure it in failover mode. Let's say you have like two data centers. You can say this is the primary one, and if something happens to it, you go to the other one. You can configure it if you have multiple, let's say a bigger one and a smaller one. You can configure it in a weighted mode. Let's say 60% goes to the bigger, 40 to the smaller in terms of the user population. Or you can configure any combination of that. For example, you can have two data centers in North America, and so you can configure North American ones, like this is a primary, this is a failover North American one, two in Europe in the same way, and so forth. Or if you're able willing to run some agent inside your data center and provide CDN with load information on the data center, then CDN can even have load as a feedback in deciding where to forward, where to send the user to. So that's one of the products that CDNs often offer is a DNS as service. And now we're coming to a question of how do CDNs work inside? So far we've been well. This is a picture that we've been looking at, and this is a picture of how Akamai CDN, as well as Google, let's say YouTube CDN, Netflix, maybe others work. We call them DNS-controlled CDNs. How do they work? You have your end-user device. It connects to a DNS server provided by the ISP. That DNS server finds a authoritative server from CDN that's probably very close by. Authoritative server knows where the user is based on where its DNS server is located, because that's what it sees. And it sends the user to the closest location, CDN location to that DNS server effectively. Now, the advantage of this, I mean, each of the architectures of CDNs have advantages and disadvantages, but the advantage is that CDN has a full control. That authoritative server knows everything about the network, about the world, about congestion anywhere, about load on every single pop, and can choose and location of content, and can choose the best pop for this particular end user for this particular website. You can create, and we do, thousands of pubs all over the world close to the end users, can support massive live events, like everybody is watching Olympics, or in India, it could be cricket, or in North America, it could be Super Bowl. Everybody is watching it at high definition, and because the data is coming from their local ISPs, there is no congestion. You can support those huge events. Now, the downside is that, of course, when you have small pubs, a lot of pubs, they have to be small. You're not going to fit long tail content. And like we said, you have to have tier distribution for that. The other downside is that with DNS managed CDNs, there are a lot of different IP addresses that you can be directed to and serve the traffic from. So it's not feasible to have some sort of an ACL to say that, hey, this particular website can only be served from that particular IP address. Sometimes it's useful. And it's useful for things like zero-rated billing, or enterprises, for example, wanting to only enable a particular website for their to be accessible from their branch. And another big problem is that there are some situations when a big multinational corporation has a centralized IT system. So you have a branch office in one continent, but DNS servers are located in a central office. So when a branch server wants to access internet, it's connecting to the DNS server in its central office, which is connecting to a CDN server near its central office. And the CDN server doesn't know that the end user is actually far away. And so it ends up serving, the CDN ends up serving the content from very far away, and that basically defeats the purpose. So there's another type of CDN that's anycast control CDNs. That's the other big CDNs today, like Cloudflare, Fastly, are built that way, and others as well. In a way, it's an easier way to build a CDN, but obviously there are some things that are hard. So the way to do it is you create, instead of thousands, you create dozens or maybe a few hundred of very large pubs around the world. All these pubs are announcing content from the same IP address, so that's why anycast. And therefore, the DNS servers just need to resolve to the same IP address no matter where you are. And you rely on internet routing, BGP, to find you the closest anycast pub. Now, the advantage is that you have bigger pubs, you can cache a lot more content right in there. Also, the echoes, like the number of IP addresses in an echo, is not a problem. I mean, you really have just one or maybe very few for a particular website. It's the same anywhere. But the downside is, like we've seen, that BGP's closest is often suboptimal and can be congested. So anycast control CDN will spend a lot of effort trying to traffic engineer BGP announcements to engineer it around the congestions. And this is a very hard problem. Is it always successful? I mean, maybe not, but again, I don't know that much about the other guys. But it definitely also requires, because BGP is not easily controllable, overbuilding capacity in each pub, because you don't exactly know how many users are going to show up, how many users BGP will bring to you. And again, you cannot have many more than a few hundred pubs, because if you start like putting them too close to each other, you're going to have BGP convergence problems. So constantly something on the internet is changing in terms of routing. Some router gets shut down for maintenance, another router stops maintenance and comes back online. The paths change. And if your routing changes in the middle of your connection and you start getting routed to a different location, it can be disruptive. It can break your connection. So, and yes, of course, since now you're not inside ISPs, you're like in internet exchange pubs. There is a question of whether you're able to serve really high bandwidth event through those internet exchange links, or you're going to be saturating them, the links to particular ISPs. Now, there is a third way, and that's actually something I was involved in about 8 to 10 years ago. That's something we built at Akamai. It's so-called a hybrid model. So what we do is you have your anycast cloud, but they contain small pubs, very small pubs. They announce the same IP address for a particular property. And but the data is still close to the end users inside your ISP. So what happens is your phone, or your client is connecting to that anycast pub, to that IP address. The server inside that pub is really acting as a very fancy router. It sees the source IP address of the connection, so it knows where you're coming from. It finds the closest CDN pub with the content, with good connectivity to you, and forwards the data, forwards all packets that you send to that location. And the data now, the actual download, the bulk of the data is served from the location right inside your ISP. So effectively, you have the long leg to the anycast pub, which contains just request headers and X, and the bulk of the data comes directly from inside the ISP. So the advantage is that it's not a problem. So DNS is not really involved in directing you. So if you have like a distributed, if you have like a localized IT infrastructure for an enterprise, that's okay, because really we're not. It's going to be the same IP address anywhere in the world, and the bulk of the data doesn't cross exchange points. It comes directly from your location. It does create a little bit longer, well, it does create longer round trips than it could have been otherwise. It's fine for videos. It's only for download heavy content, of course. It's not for upload, because the whole point is that the download is happening directly. And the biggest problem is that effectively what's happening is the edge location needs to send traffic claiming to come from the anycast IP address, so that the end user sees it as a single connection. And the edge location is not really advertising that anycast IP address over BGP to the network, so it looks like it's spoofing it. Some anti-spoofing filters may prevent us to be able to deploy this service in those locations. All right, so there are other topics for CDN that we haven't had time to cover today. There is a lot more in terms of security products. So security products is now one of the biggest things that CDNs do. It deserves its own lecture. Another product CDN often does is a content storage product. So, for example, if you have a big media library, instead of having to load it on demand from origin servers, the media owner can push it to the CDN in advance. So CDNs provide storage products. Data analytics is very important to many customers, and it's very varied, and CDNs let you do it. VPN services, CDNs provide those as well. There are networks as a service is another kind of service that one can provide. So effectively, if you're an enterprise and you want to be able to talk to from your branch to your head office, and you don't care about any public website, that you just want to accelerate your own internal applications, CDNs let you do that. And there are many other products. Looking at the future, so I can totally see a lot more work done with customer code at the edge. It's obviously very popular. It's very effective. There will be a lot of more ways for customers to provide their own code to run that is more customer friendly. AI inference at the edge. It's a very interesting opportunity that we see some need for it right now, and I'm sure CDNs would be happy to play in that space. Some of the bigger customers require custom solutions at the edge, and CDNs do that already. If you've heard of Apple has iCloud Private Relay, for example, as a product that has custom implementations by a number of CDNs to support that use case, Akamai included. And so such custom use cases could definitely be something that CDNs do in the future. Cloud computing and CDN integration, that's happening today, that will continue in the future. Most of the origin places servers for content websites are in the clouds, like some of the public clouds, and making sure that those origins can be accelerated and can be delivered that content faster to the end users requires is helped by integration between the cloud providers and CDNs. A lot more work with that's facilitated by QUIC and HTTP3. There are websites already been served by QUIC and HTTP3, but QUIC technology can do a lot more than that, than just simply serve websites, and we're taking advantage of. And obviously, in the future, there may be a lot more things that we don't see, or I cannot see yet today, but the future will show. And this is the end for today. Thank you, everybody.
Thank you so much, Igor. That was fascinating. There are quite a few questions. Let me go ahead and go through some of them. Guys, if you have other questions too, please go ahead and post. So some of them I'm gonna save them for you for the you can they're offline because they're a little more complicated than for a general audience. But one I think is quite interesting is can you talk a little bit about load balancers and QUIC? What is your thought? I guess also too, I know a lot of our enterprises are blocking QUIC. Maybe that's changing now, but some of you guys who are with enterprises, maybe you can talk to that too. But yeah, so what are your thoughts, Igor?
Sure. So let me take it actually the last thing first. QUIC was designed with basically three key ideas in mind. So number one, it's very technical, not controversial. Make it faster than TCP. Solve the number of problems that is with TCP, so head of line blocking and some other things. But second thing that QUIC was designed for is to ensure complete privacy and anonymity for the complete privacy for the end users. But privacy means, well, privacy security, and to be able to provide that in effectively hostile environments where there is surveillance. Now, that's probably the biggest issue that enterprises have with it, because it's not as easy to do inspection and to figure out what's going on. Now there is still SNI that is available in clear text, just like with TCP. But the third thing is for QUIC, it was developed basically trying to avoid what we call protocol ossification. So effectively encrypt everything to prevent devices from being able to identify any features of QUIC as particular as QUIC, and therefore prevent QUIC from changing in the future. So I'm sure that enterprises find it difficult to control this traffic. It does look like effectively random UDP traffic. It's hard to tell whether it's an attack or legitimate traffic, but that's by the nature of QUIC. So that's possibly where some of the initial, and of course, none of the existing systems that were trying to inspect traffic, control it, intrusion protection, intrusion detection, systems like that would work with QUIC. So I'm sure that's probably one of the reasons why enterprises are reluctant to adopt it or have been up to the point. Now, load balancers and QUIC. So first of all, inside CDNs, so clearly there are many servers, backend servers behind like a particular IP address. Usually CDNs have their own proprietary implementations and that you work with QUIC, but in a proprietary way. There is a IETF work to make a standards-based load balancing for QUIC so that different web servers are able to understand this load balancing protocol and handle that. I don't think this work has been published as an RFC yet.
Great, great. Thank you. Yeah, we've got so many questions here. So let me get to another one. So how is the content from various providers kept private, safe, and isolated?
Very good. That's a great question. So first of all, so CDNs, I mean, that's kind of the job to make sure that they serve only the cached content. If you're talking about the cached content on disk, correctly, the correct content provider. If we're talking about, again, and now I have to talk about Akamai implementation, a little bit under the covers. So effectively on disk, every block that's stored on disk has a header that actually tags it with a correct, with an internal ID that corresponds to the particular origin. So even if disk is misbehaving, we're not going to serve somebody else's content by mistake because that tag is verified that whatever is coming from disk. Now, on the network itself, it's going to be the same servers that are serving content for many different websites. And those servers will have certificates that are for each particular website that needs to be served. So that's kind of a CDN's job to make sure that it doesn't mix up content for different providers. I mean, so hopefully we're doing a good job at it.
Yeah, no, I mean, if you're not doing that, I'm not sure what you are doing.
Right.
Yeah.
Well, but like I said, the thing about, I mean, the thing about faulty disks, I mean, everything, having hundreds of thousands of servers for many years, everything has happened. And long time, like over a decade ago, we've had an incident when a faulty disk was serving blocks belonging to different content. So some corruption in the file system that went undetected. And so, like I said, right now, at least for Akamai, every single block of disk is verified that it belongs to the correct, basically, web object.
Yeah, no, we could talk about this for a long time because I know one time I had a virtualized hosting service, one of those little hosting services. And when I did an ICMP, a multicast ping, I could
Mhm.
see everybody else who was had also rented space. So that's a whole nother topic. But it leads to another question, which is are you using multicast in the internals of your CDNs?
So we do not use multicast. So multicast is a protocol. So we don't. Well, let's put it this way. Sorry, there are two different types of multicast when people are talking about multicast. There is an internet multicast, which basically means multicast that you have nodes on the internet that are publish, subscribe for multicast channels. And there is a multicast at a technology, layer 2 technology, like within the single broadcast domain. So, I mean, effectively, broadcast is a kind of a, just when you do layer 2 broadcast, it's kind of multicast. And in IPv6, actually, they just call it multicast. So yes, we do multicast in terms of layer 2 between our servers, but we don't do multicast on CD, like basically internet, the internet multicast. It needs support from multiple ISP providers. There've been some efforts to explore that, but that really didn't pan out in anything that beyond one or two ISPs were willing to support.
Great. Well, we're running out of time. Really great presentation, Igor. And I know I would love to hear more on some of the various topics you mentioned. Guys, send me an email or put it in the chat window or whatever. If you guys want to hear more on this area, I know it's very, very interesting, certainly. Um, and Igor, you present so beautifully that I can actually understand what's going on. So,
Thank you.
uh,
So yeah, Nalini, and if you want to send me a list of all the questions, I will be more than happy to answer them offline, and maybe you could post the answers for people who are interested.
Perfect. Thank you. Yes, we'll get everything from the chat window and I'll send you. So guys, yeah, it's great to have so many questions. So Igor will answer them offline. So thank you again. And so the next presentation in November was supposed to be from NIST, the National Institute of Standards and Technology in the United States. And it's a bit problematic because the US government is still shut down. And so let's see what happens, but we may prevail on Igor again if he's got some time. And I can't because I can't get, as I say, anyway, it's chaos. You know, so let's see what happens. But thank you guys again. And if you have any more questions or anything, do please let us know. So thanks again. Okay. Until next time.
Thank you.
Bye.
Bye.